Woohoo! I'm live, and this is Math 40, section 5.20, and negative exponents. And some of you are like, what? You can have zero and negative exponents? And I'm going to say, yes, let me show you why. La la la. Okay, so what we're going to start off with is just a reminder that if I have 2 to the 5th power, that's 2 times 2 times 2 times 2 times 2 times, whoops, 1, 2, 3, 4, 5. Oh, apparently someone went above and beyond. Look over there. Is that a pterodactyl? Oh, sorry. It must not have been. Okay. So yes, now you can see very clearly that I wrote 2 times 2 times 2 times 2 times 2. 5 of them, right? So if I've got 2 to the 5th power, this is this, which equals 32. Now what I want to do is look at what 2 to the 4th is. Okay, let's see. This is going to be my big test. Can I count to 4? Yes! I believe I successfully counted to 4. This is 2 times 2 times 2 times 2. That's 16. Now, you're going to say, well, duh. And I'm going to say nice, because that means you've been learning your exponents. But what is really important is not actually either of these, but the pattern that they set up. So let's take a look at the pattern here. As I go from 2 to the 5th to 2 to the 4th, what changes? You're right. I went from 5 to 4 in the exponent. So the exponent decreases by 1. I could have decreased by anything. I choose to decrease by 1 for reasons only I understand right now, possibly. You might have already seen this, in which case you're going to be like, oh, I know where you're going with this. Over on the other side, now this is a hard question to answer because you haven't seen the pattern yet. But if I say, how do you get from 32 to 16? There are a lot of ways to get from 32 to 16. You could subtract 16. You could add 100 and then subtract 116. You could divide by 48 and then multiply by 48 and then divide by 2. There are a lot of things you could do. What I'm looking for is, would you believe me if I said we divided out one of the 2's? So what I'm saying is, as the exponent decreases by 1, we're basically taking back a 2. So in our pattern, if I'm going to follow it, the next one is 2 cubed. 2 times 2 times 2, which equals 8. So over here on the left, do we stick to the pattern? Yeah, the exponent decreased by 1. And over here, if I go from 16 to 8, am I dividing by 2? Absolutely. Now we have a pattern that seems to be sticking. Now, the thing is, in math, to actually prove this pattern, we would have to be pretty much immortal and show this for all possible numbers, which would take a long time. Longer than I have, longer than my kids have. So what I'm going to say is we're just going to look at the pattern, and then you're going to know that I'm going to tell you that this pattern holds. So we're not really proving that the pattern holds. We're just looking at it. It's an important distinction. 2 squared. I decrease the exponent by 1. I get 4. Is that, again, dividing by 2? 8 divided by 2 is 4. Nice. Let's keep going. 2 to the 1st power, that's just a 2. 4 divided by 2 is 2. I decrease the exponent by 1. And you guys are all going, yeah, this is great. Why'd we do it? And the answer is because I'm going to keep going. And I think a lot of reasonable people would be like, what? And I would say, yeah, totally. Let's do it. Let's go to 2 to the 0th. Now, am I following the pattern? I went from 5 to 4, from 4 to 3. These are the exponents. From 3 to 2, from 2 to 1, from 1 to 0. I'm following the pattern. I'm subtracting 1 every time. Okay, so how do you write 0 2's multiplied together? The answer is, who knows? This is no longer that same definition. Now we're looking at a pattern rather than an actual definition or a meaning of an exponent. So this is the pattern that the exponent follows, not the actual meaning. Because, you know, if you say you have 0 2's multiplied together, I would say, I don't know what that would be. What else is there? So let's take a look. Now, this is where things get interesting. I am going to say, well, wouldn't it be nice if exponents kept following the pattern, even though we're not really sure what this thing would look like? Wouldn't it be lovely if this just kept working? We just pretend the middle part doesn't matter and we keep doing the outside parts. Let's try it. So what is 2? 2 divided by 2 is, you got it, 1. So I'm going to say that 2 to the 0th power, weirdly enough, is 1. Now, it's not just me saying this. This is something that mathematicians have been playing with and postulating and suggesting and arguing about and talking for a very long time. So this is not just a brand new concept. This is old. And in fact, we do define it this way. Anything to the 0th power except for a 0. Now, why couldn't 0 play this game? Why don't they're going to be held out of the reindeer games? Because part of this pattern was dividing by 2. So if my base were 2, I'd have to be dividing by 0, which, wow, that would be a whole lot of other stuff that we're just not ready to deal with right now. So we're going to leave that be. So it's only numbers that aren't 0, but follow this pattern. Anything to the 0th power except for 0 equals 1. But I'm not going to stop there because, patterns. What's the next one? What would the exponent be? Dora style. You're right. I'm going to keep subtracting 1, so I get 2 to the negative 1. Again, I really don't know what this would be. The representation of an exponent, we're so far out of that 2 negative 1 2's multiplied together, what does that equal? It's starting to get weird. But over here, the pattern is I just divide by 2. What's 1 divided by 2? It's 1/2. Now here's where things get interesting. 2 to the 0th is 1. 2 to the negative 1, 2 to the negative 1 or 2 to the negative 1st is 1/2. It's almost like the 2 got stuck in the denominator. Next up, 2 to the negative 2 or 2 to the negative squared or however you want to say it. That's some weird stuff going on. We don't know what it represents, but I will say I'm going to divide by 2 again. Now, this is hard to do, taking a fraction and dividing by 2. I will remind you, here, I'll write these in. 1 divided by 2 is 1/2. That's just kind of how fractions work. That's the definition of a fraction. 1/2 divided by 2. Now, this is something that's more complicated. I'm going to have to remind you about fractions. That's 1/2 divided by 2 over 1, which is 1/2 times 1/2, which is 1/4. So this is going to be 1/4, this guy. 2 to the negative 2 is 1/4, which is really 1 over 2 squared. Now, this is starting to get really interesting. So in other words, if I have negative exponents, it works just like positive exponents. 2 squared gave me 4 up here. 2 to the negative 2 gives me 4 in the denominator. So negative tells me we're in a different place. We're not upstairs, we're now downstairs. So let us review. The rules with the happy spider. A to the 0 equals 1 when a is not equal to 0. 0 to the 0th power is undefined, which just means we're not saying what it is. It might mean you might learn it later. It might mean nobody knows what it is. But for right now, we're going to say it's undefined. Let's just not go there. A to the opposite of n is 1 over a to the nth. And if we have a to the negative n or a to the opposite of n in the denominator, it pops up and it changes sign. So now we have an interesting thing. Exponents. If we have a negative exponent, it means you're in the wrong place, which opens us up. I think I'm going to stop this video now because it's gotten kind of long, and then we'll approach page 2 separately. But now we get to talk about, you got it, of course, vampire math. Woohoo! I'll see you in the next video for vampire math.